What if the next mass extinction isn't millions of years away? What if it's already in motion, barreling toward us right now, invisible to the naked eye, but powerful enough to reshape life on Earth forever? It's not the plot of a science fiction film. It's a scenario rooted in cold, measurable science. A planet-killer asteroid is not just theoretical. It is real, it is tracked, and it is terrifying. A planet-killer asteroid is exactly what it sounds like, an object large enough to trigger a global catastrophe upon impact. These massive space rocks, typically larger than 1 kilometer in diameter, possess the energy to wipe out entire ecosystems, plunge the planet into a nuclear winter, and collapse civilization as we know it. One such asteroid, estimated to be over 10 kilometers wide, struck Earth 66 million years ago and ended the reign of the dinosaurs in a matter of hours. Today, scientists have given similar objects a modern name: extinction-level threats. Right now, multiple known asteroids are under constant watch. Among the most concerning are 1950 DA, Apophis, and Bennu. Each one follows a path that brings it worryingly close to Earth's orbit. Bennu, in particular, has captured headlines after NASA confirmed it has a real, albeit small, chance of colliding with Earth in the 22nd century. Apophis is expected to pass within just 31,000 kilometers of our planet in the year 2029, closer than our own geostationary satellites. And 1950 DA. That one has scientists debating probabilities of impact in the year 2880, and its trajectory still raises uneasy questions. But these are just the known threats. What about the ones we haven't seen yet? The truth is, only a fraction of near-Earth objects have been discovered and mapped. Thousands remain hidden in the darkness of space or camouflaged by the blinding light of the sun. And all it takes is one rogue asteroid. One unpredictable change in trajectory. One cosmic bullet we never saw coming. In this video, you'll uncover the most shocking truths about these celestial threats. We'll dive into the historical impacts that have already reshaped our planet, like the Chicxulub asteroid that triggered the dinosaur extinction. We'll explore the latest missions NASA and global space agencies are launching to try to deflect potential collisions. You'll hear the terrifying energy calculations of what happens if one hits land, or worse, the ocean. You'll learn about the blind spots in our defense systems and the uncomfortable reality that we may not be prepared for what's out there. You'll also discover how objects like Apophis and Bennu became household names in the world of planetary defense, and why experts warn that human civilization is still not taking the threat seriously enough. This isn't just a story of science. It's a story of survival. And the clock is ticking. This isn't just about what could happen. It's about what will happen, eventually. Whether it's in 10 years, 100, or 1,000, a planet-killer asteroid is coming. The only question is, will we see it in time? And if we do, can we stop it? Keep watching. The answers may shake you to your core. What is a planet-killer asteroid? In the vast silence of space, there exist objects so powerful that their very presence near Earth stirs anxiety among scientists. These are not ordinary space rocks. They are massive, ancient remnants of the early solar system, celestial time bombs moving silently through space, carrying the potential to extinguish life as we know it. These are planet-killer asteroids. A planet-killer asteroid is defined by more than just size. While the minimum threshold for global catastrophe typically begins with objects larger than 1 kilometer in diameter, the true classification involves a combination of size, speed, density, and impact angle. These factors combine to determine the kinetic energy released upon collision. And when we talk about energy in this context, we're not speaking in mere kilotons or even megatons. We're speaking in millions of megatons. A single planet-killer asteroid striking Earth could release energy equivalent to several million nuclear bombs detonating at once. To put that into perspective, consider that the asteroid responsible for the extinction of the dinosaurs was estimated to be around 10 kilometers wide. When it slammed into what is now the Yucatan Peninsula, it released the energy equivalent of more than 100 trillion tons of TNT. That wasn't just an explosion. It was an extinction event. Temperatures soared across the globe, wildfires ignited in an instant, and a blanket of dust and soot choked the atmosphere for years. Sunlight disappeared, crops failed, food chains collapsed. It wasn't just the end of a species, it was the end of an era. But not all large asteroids trigger global disaster. Scientists often distinguish between regional and global extinction threats. A smaller object, perhaps between 300 to 800 meters in diameter, might level a city or devastate a country. The Tunguska event in 1908, while much smaller in scale, is a chilling reminder of that possibility. That asteroid or comet fragment exploded over Siberia, flattening more than 2,000 square kilometers of forest. Had it struck a populated area, it would have killed millions in seconds. Yet it was only estimated to be about 50 to 100 meters wide, far smaller than a true planet killer. A planet killer, by contrast, affects the entire globe. Its effects are not measured in miles but in hemispheres. These objects don't just cause craters, they alter climate systems, ignite planetary fires, and threaten the continuation of advanced life. A 1-kilometer asteroid is enough to cause a multi-year nuclear winter, disrupt ocean currents, and collapse the agricultural systems that sustain human civilization. Several real-world asteroids fall into the category of potential planet killers. One of the most well-known is Asteroid Bennu, which is approximately 500 meters wide and has been monitored closely by NASA due to its projected close approaches to Earth in the late 2100s and early 2200s. While its current risk rating has been downgraded, even a near miss raises questions about our readiness. Another object, Apophis, is roughly 370 meters wide and will pass shockingly close to Earth in 2029, close enough to fly underneath our satellite systems. And then there's 1950 DA, a behemoth over 1 kilometer wide, with a non-zero chance of striking Earth in the year 2880. The danger may lie far in the future, but the threat is real and mathematically measurable. The destructive power of these asteroids comes from kinetic energy, energy in motion. The formula for calculating that energy is simple in physics, but devastating in consequence: half the mass multiplied by the velocity squared. Because these objects travel at speeds exceeding 20 kilometers per second, even a relatively small asteroid becomes a doomsday device on impact. The energy released doesn't just tear into the Earth's crust. It vaporizes everything in its path, generates global shockwaves, and launches debris into orbit, where it rains back down across the planet like a second wave of fire. In practical terms, the explosion from a 1-kilometer asteroid could dwarf the largest nuclear weapon ever detonated by a factor of tens of thousands. And while humanity has built powerful tools of war, nature's arsenal remains unmatched. We have never detonated anything remotely close to the force a true planet killer would unleash. Our most powerful bombs can destroy cities. A planet killer destroys the world as we know it. Understanding the nature of these threats is the first step in preparing for them. These are not just theoretical concepts or Hollywood inventions. They are measurable, trackable, and entirely within the realm of possibility. And as our ability to detect them improves, so too does our understanding of just how many are still lurking in the shadows of space. Earth's impact history: what came before? Long before telescopes and tracking systems, long before satellites orbited the planet or humans understood the mechanics of the cosmos, Earth was already locked in a deadly dance with asteroids. The history of our planet is written not just in the movement of tectonic plates or the slow carving of glaciers, but also in sudden, violent impacts that have reshaped continents, altered climates, and extinguished entire species in the blink of a geological eye. Perhaps the most infamous of these events is the one that brought an end to the age of dinosaurs. Roughly 66 million years ago, a massive asteroid, estimated at around 10 kilometers in diameter, slammed into what is now the Yucatan Peninsula in Mexico. The impact created the Chicxulub crater, a structure over 180 kilometers wide, buried beneath the surface but unmistakable in geological surveys. The force of that impact released more energy than all the nuclear weapons on Earth combined, igniting global wildfires, triggering tsunamis hundreds of meters high, and sending vast amounts of debris into the atmosphere. The resulting cloud of dust and sulfur dioxide blocked sunlight for years, plunging the planet into darkness. Photosynthesis ceased, temperatures dropped, and ecosystems collapsed. The dinosaurs, along with nearly 3/4 of all species on Earth, vanished. That moment remains one of the clearest and most terrifying examples of what a planet-killer asteroid can do. But while the Chicxulub event stands as the ultimate cautionary tale, it is far from unique. More recently, and on a much smaller scale, Earth experienced the Tunguska event in 1908. In the early morning hours of June 30th, a mysterious explosion occurred over the Siberian wilderness. The object never even touched the ground. It exploded in the atmosphere at an altitude of about 5 to 10 kilometers. Yet the shockwave flattened an estimated 2,000 square kilometers of forest, toppling over 80 million trees. Witnesses reported seeing a fireball streak across the sky, followed by a sound like artillery fire. Seismic instruments registered the blast thousands of kilometers away. Scientists later estimated that the explosion released energy equivalent to at least 10 to 15 megatons of TNT, about 1,000 times more powerful than the atomic bomb dropped on Hiroshima. And then there was Chelyabinsk. On the morning of February 15, 2013, without any warning, a 20-meter-wide asteroid entered Earth's atmosphere over Russia at a speed of nearly 70,000 kilometers per hour. It exploded mid-air with the force of about 500 kilotons, over 30 times the energy of the Hiroshima bomb. The shockwave shattered windows across 6 cities and injured more than 1,500 people, mostly from flying glass. What made Chelyabinsk particularly disturbing wasn't just the explosion itself, it was the fact that it came from the direction of the sun, making it invisible to ground-based telescopes. Humanity had no idea it was coming until it was already in the sky. These events are not isolated anomalies. Across the globe, scientists have identified more than 190 known impact craters, some ancient, others relatively recent. These craters are scars left behind by cosmic collisions, found on every continent except Antarctica. In places like Arizona's Meteor Crater, Canada's Manicouagan structure, or South Africa's Rudderfort Dome, the physical evidence of past impacts is undeniable. Fossil records in these regions often show abrupt shifts in biodiversity, hinting at the broader ecological consequences of those collisions. Statistically, Earth is no stranger to asteroid strikes. Large impacts, those capable of regional or global devastation, follow a pattern, an unsettling one. Based on crater evidence and geological analysis, scientists estimate that a 1-kilometer asteroid strikes Earth on average once every 500,000 years. Planet killers, the kind responsible for mass extinction, might strike once every few million years. That may seem like a long time, but in planetary terms, it's the blink of an eye. And when we line up those past impacts on a timeline, a chilling pattern emerges. We are, by all estimates, overdue. This isn't alarmism. It's math. The fossil record and geological evidence tell us that massive impacts have happened before and will happen again. The question isn't if, but when. And unlike past extinctions, we now have the tools to detect these threats before they strike. But detection is only half the battle. History shows us that the universe doesn't play favorites. It has erased species before and could do so again. Earth's past is filled with craters, and if we're not prepared, one of them could define our future. The current threats being tracked as our technological capabilities have grown, so too has our ability to peer into the vastness of space and track the countless objects that orbit the sun. Among these are the near-Earth objects, or NEOs, asteroids and comets whose paths bring them within 1.3 astronomical units of Earth's orbit. While most of these celestial visitors pose no immediate danger, a select few carry with them the potential to alter life on this planet forever. NASA, along with other space agencies worldwide, has taken up the monumental task of identifying and monitoring these threats. But even with state-of-the-art technology, many questions remain unanswered, and many dangers still hide in plain sight. NASA's Near-Earth Object Observations program is responsible for cataloging these potential threats. It operates a comprehensive watchlist that monitors thousands of NEOs, focusing particularly on those classified as potentially hazardous asteroids. These are objects that come within 0.05 astronomical units of Earth and are larger than 140 meters in diameter, big enough to cause regional devastation, if not more. This list is constantly updated as new objects are discovered and existing trajectories are refined. The goal is clear: find them early, assess the risk, and develop strategies to deflect or avoid catastrophe. Among the most famous names on this list is Apophis. Discovered in 2004, this asteroid sent shockwaves through the scientific community when initial calculations suggested a significant chance of Earth impact in 2029. Although later analyses ruled out that specific impact, Apophis remains a source of concern. On April 13, 2029, it will pass just 31,000 kilometers from Earth, closer than many of our satellites. The sheer proximity of this flyby makes Apophis a critical case study in orbital prediction and planetary defense. A slight shift in its trajectory, caused by gravitational interaction or other subtle forces, could dramatically alter its long-term path. Another object drawing international attention is Bennu, an asteroid roughly 500 meters in diameter. Bennu is particularly significant because it has been the focus of a direct mission, NASA's OSIRIS-REx spacecraft, which successfully collected samples from its surface and is bringing them back to Earth. Bennu's orbit intersects with Earth's every 6 years, and while the probability of a direct hit is low, there is still a measurable chance of impact in the year 2182. That's more than a century away, but in terms of planetary defense, it is uncomfortably close. And then there is 1950 DA, one of the most ominous entries in NASA's database. First observed in 1950 and rediscovered decades later, this asteroid is over 1 kilometer wide, large enough to qualify as a planet killer. Its projected trajectory shows a possible impact with Earth in the year 2880. While that date is centuries in the future, the object's velocity and orbit make it a serious subject of study. It is one of the few asteroids with a calculated impact probability, albeit small, that scientists cannot entirely dismiss. To quantify these risks, scientists use a system called the Torino scale. This scale ranges from 0 to 10 and measures the potential hazard of impact events. A rating of 0 means no risk, while a rating of 10 indicates certain global catastrophe. Most NEOs rank as 0 or 1, posing no real danger. But even a rating of 2 or 3 triggers detailed analysis and global attention. For a time, Apophis ranked at level 4, the highest rating ever recorded, before further observations allowed scientists to downgrade its threat level. The Torino scale combines impact probability with kinetic energy potential, offering a balanced view of both likelihood and consequence. NASA's Sentry system is another essential part of this tracking effort. It's an automated, highly sophisticated monitoring system that continuously scans for possible future Earth impact events from newly discovered asteroids. It runs simulations, recalculates orbits, and updates predictions as new data becomes available. What makes the Sentry system powerful is its ability to model not just years into the future, but centuries, using the best available measurements. Yet even this advanced technology has its limits. Predicting the path of an asteroid is not an exact science. One of the biggest challenges is a phenomenon known as the Yarkovsky effect. This is a small but persistent force that affects an asteroid's orbit over time due to the way it absorbs sunlight and re-emits that energy as heat. The process causes a subtle but cumulative push on the asteroid, altering its trajectory in ways that are extremely difficult to calculate with precision. Over decades or centuries, the effect can shift an asteroid's path enough to change its impact probability dramatically. The longer the projection, the more uncertainty creeps into the equation. Orbital drift, gravitational influences from other celestial bodies, and even the shape and spin of the asteroid itself all contribute to prediction challenges. An asteroid might be on a perfectly safe trajectory today, only to have its orbit nudged slightly by a gravitational slingshot from another planet, or by a thermal push from the Sun, sending it on a collision course a century later. This uncertainty is why even low-probability objects remain on NASA's watch list and why close flybys, like Apophis in 2029, are monitored with such intensity. Several upcoming close approaches are already marked on scientific calendars. In 2029, Apophis will give us a once-in-a-lifetime opportunity to observe an asteroid passing within satellite range. In 2036, another object, currently of low concern, will pass near Earth and offer additional data. These events are not just astronomical spectacles. They are critical chances to test our tracking systems, refine our models, and prepare for the day when a flyby might become a bullseye. While none of the current objects under surveillance are expected to strike Earth in the immediate future, the key word remains expected. The science of asteroid tracking has improved dramatically, but it is still a work in progress. The more we learn, the more we realize how much remains hidden. Some threats can be forecast decades in advance. Others, like Chelyabinsk, arrive without warning. And that duality, of known danger and unknown risk, is what makes this issue so urgent. The sky is full of motion. The solar system is not a static place. Each asteroid we discover is a clue to a puzzle we're racing to solve. And as we continue tracking known threats like Bennu, Apophis, and 1950 DA, we must also remain vigilant for what we haven't yet seen. Because it's not just the objects we're watching that could change our future. What would happen if one hit us? When people imagine the impact of a large asteroid hitting Earth, the image often involves an explosion, a massive crater, and maybe a few crumbling buildings. But the reality of such an event is far more catastrophic. The moment an asteroid reaches planet killer scale, its arrival triggers a chain reaction that goes far beyond the initial blast. The destruction radiates across borders, oceans, and ecosystems, reshaping not just the land it strikes, but the atmosphere, the climate, and every thread of modern civilization. The outcome depends heavily on where the asteroid lands. A strike on land is immediate and visceral. Upon entry into the atmosphere, the object superheats the surrounding air, creating an intense flash of thermal radiation. Temperatures rise so quickly that everything within a large radius of the impact zone ignites instantaneously. Forests burst into flame, structures disintegrate, and anyone caught within the blast radius suffers fatal burns before the shockwave even arrives. That shockwave, moving faster than sound, flattens everything in its path. Buildings crumble, glass shatters, roads split apart. The ground quakes with the force of a high-magnitude earthquake, radiating energy outward from the crater for hundreds of kilometers. But a direct hit on a city would be even worse. Urban areas, densely packed with infrastructure, fuel, and people, would turn into a furnace. Hospitals, emergency services, and communication systems would be the first to collapse. In the first few minutes alone, the death toll could reach into the millions. And those who survived the blast wouldn't be out of danger. Fires, toxic smoke, and structural collapses would make rescue efforts nearly impossible. Survivors would find themselves stranded in a world that no longer resembles the one they knew. If the asteroid strikes the ocean, and considering Earth is mostly covered in water, this is statistically more likely, the devastation takes a different shape, but the outcome is no less terrifying. The impact would displace trillions of gallons of water in an instant, sending shockwaves through the sea that travel faster than any submarine. Gigantic tsunamis, potentially hundreds of meters high, would ripple outward in all directions. These waves would strike coastlines with unimaginable force, washing away entire towns and cities, dragging debris, vehicles, and people deep into the sea. The global shipping industry would be paralyzed, and port cities, many of which are major economic hubs, would suffer irreversible damage. Inland regions, too, wouldn't be spared, as secondary flooding and infrastructure collapse would spread the chaos. Regardless of where the asteroid lands, the atmosphere would be the next victim. Upon impact, vast amounts of vaporized rock and debris would be ejected into the stratosphere. If the object were large enough, this material would block sunlight from reaching the Earth's surface for months, even years. This is the basis of the nuclear winter theory, a scenario where sunlight is obscured by dust, temperatures plummet globally, and agriculture collapses. Crops would fail not only due to lack of light, but also from sudden and prolonged temperature drops. A global food shortage would set in quickly. The collapse of pollinator populations, like bees, would compound the agricultural disaster, and the food chain would begin to unravel from the bottom up. Scientific models that attempt to estimate the human cost of such an event vary depending on the size and location of the impact. However, simulations of a 1-kilometer asteroid strike suggest that initial fatalities could exceed 10 million if a major city or coastal region was struck. In the months that follow, indirect deaths from famine, disease, economic collapse, and social unrest could push the number into the billions. Even in the best-case scenario, where international cooperation and emergency response are perfectly coordinated, the global economy would be devastated. Supply chains would shatter, financial markets would plummet, and entire industries, especially agriculture, energy, and transportation, would face collapse. Society itself would be tested in unprecedented ways. Mass migrations would begin as populations fled the most devastated areas. Governments would be forced to ration resources, and civil unrest would erupt in places where food and clean water became scarce. In regions not directly impacted by the blast or fallout, the economic and social ripple effects would still be severe. No country would remain untouched. The psychological toll of such a disaster, with billions experiencing loss, fear, and uncertainty, would be incalculable. And yet, even in the worst moments, there would be remnants of hope. Some simulations show that if the impact zone is isolated enough, such as an unpopulated area or remote ocean, combined with strong global coordination and long-term emergency planning, humanity could survive. But survival would not mean comfort. It would mean decades of rebuilding, adapting to a colder and harsher planet, and redefining every aspect of modern life. The best-case scenario still includes global famine, a crashed economy, and a population forever changed by the knowledge that extinction once knocked on the door. The difference between best and worst-case outcomes lies almost entirely in timing and preparedness. If an impact were to occur without warning, humanity would have no time to react. There would be no evacuations, no global plans deployed, no satellites repositioned to study the event. But if we detect the threat early, years or decades in advance, there is a chance to act. There is a chance to avoid the strike altogether. That is the thin line that separates a catastrophe from a controlled disaster. It is a line defined by time, science, and the will to prepare before the sky falls. Can we stop it? Deflection strategies and mission. When faced with the terrifying possibility of a planet-killer asteroid hurtling toward Earth, the most pressing question becomes not what happens if it hits, but whether we can stop it in time. Fortunately, this isn't science fiction anymore. The global scientific community has already taken its first major steps toward building a planetary defense system. The question is no longer about possibility, it's about timing, resources, and commitment. The idea of defending Earth from incoming asteroids has evolved dramatically over the last few decades. For much of human history, such events were considered acts of nature, unstoppable, unpredictable, and beyond our control. But today, scientists are developing concrete methods to prevent a collision. These strategies fall into several categories, each offering a different approach to changing the course of a dangerous object before it reaches us. The goal isn't to destroy the asteroid but to alter its trajectory just enough so it safely misses Earth. A change of even a few millimeters per second, made early enough, can translate into thousands of kilometers of distance over time. NASA's DART mission, Double Asteroid Redirection Test, was the first real demonstration of this concept. Launched in 2021, DART targeted a small moonlet named Dimorphos, which orbits a larger asteroid called Didymos. The mission's goal was to slam a spacecraft into Dimorphos at high speed to test whether its orbit could be altered. In September 2022, DART successfully impacted the target. The results were not only successful but historic. The orbit of Dimorphos changed by more than 30 minutes, exceeding expectations and proving that kinetic impactors, essentially hitting an asteroid with a spacecraft, can work. This marked the first time humanity had ever changed the motion of a celestial body. It was a breakthrough in planetary defense. Kinetic impactors are the simplest concept on the table, but they're not the only one. Another strategy involves nuclear deflection. Contrary to popular belief, this doesn't mean blowing up the asteroid Hollywood style. Instead, a nuclear device would be detonated near the surface to create an intense burst of heat and radiation, vaporizing part of the asteroid's surface and creating thrust. That small but powerful push could shift its orbit over time. This method is particularly valuable for larger or more massive asteroids that kinetic impactors alone couldn't budge. Then there's the idea of gravitational tractors. This concept involves placing a spacecraft in close proximity to the asteroid and letting gravity do the work. The mutual gravitational attraction between the spacecraft and the asteroid creates a slow but steady pull, gently nudging the asteroid off course. While this method takes longer and is best suited for early intervention, it has the advantage of being highly controlled and precise. It's a strategy that could be deployed decades in advance, given the right detection systems and planning. All of these methods share one critical dependency: time. The earlier we detect a potential threat, the more options we have to stop it. A small push applied 20 years in advance can achieve the same result as an enormous force applied just months before impact. This makes early detection the most vital element in planetary defense. Without enough time, even the best technology in the world won't be able to prevent disaster. That's why NASA and other agencies are racing to improve asteroid detection systems, using ground-based telescopes, space-based observatories, and advanced algorithms to scan the skies constantly. Planetary defense is not a challenge any one country can tackle alone. The European Space Agency is already working on a follow-up mission called Hera, which will revisit the Dimorphos Didymos system to study the long-term effects of DART's impact. China has also announced plans for its own deflection test missions, including a proposed impactor mission targeting the potentially hazardous asteroid 2020 Peter Newton's 1. Russia, too, has expressed interest in planetary defense research, though its efforts have been less public and less collaborative. These international projects show that global cooperation is both possible and essential. An asteroid doesn't care about borders, and a threat to one is a threat to all. Despite these promising developments, the world still faces serious challenges in preparing for a real threat. One of the most pressing is funding. Planetary defense programs often struggle to secure consistent financial support. Missions like DART cost hundreds of millions of dollars, a small price when compared to the cost of rebuilding civilization, but a hard sell for governments with competing priorities. When disaster hasn't happened yet, it's difficult to convince policymakers to invest in prevention. It's a problem of perception, not capability. Public awareness is another obstacle. While major space missions occasionally make headlines, the average person knows little about the real risks posed by near-Earth objects. This lack of awareness translates into a lack of pressure on political systems to act. Without widespread understanding of the threat, the push for proactive solutions loses momentum. Scientists and space agencies know what needs to be done, but without global demand for action, plans sit idle, waiting for the right moment, or the right disaster, to justify them. Political will is the final and perhaps most complex barrier. Planetary defense requires long-term vision and international coordination. It demands shared data, joint missions, and mutual trust. In a world where geopolitical tensions often get in the way of collaboration, building that unity is no small task. But the consequences of inaction are too severe to ignore. A single strike could undo centuries of progress, destroy economies, and reshape the human story in an instant. Stopping a planet-killer asteroid is possible. We have the science, we have the tools, and we've already taken the first critical steps. What we need now is urgency. Because while space may move slowly by human standards, the countdown begins the moment a threat is discovered. And if we wait too long, the question won't be whether we could have stopped it. It will be why we didn't. The scary truth: what could go wrong? Even with our advanced tracking systems and growing planetary defense strategies, the threat of a planet-killer asteroid is far from contained. One of the most chilling realities is that many of these objects can still approach undetected. Our greatest blind spot is the region of space that lies in the direction of the Sun. Asteroids coming from that angle are nearly invisible to ground-based telescopes until they're alarmingly close. The Chelyabinsk meteor in 2013 came from this sun-facing direction, catching everyone by surprise and highlighting just how vulnerable we still are. Even more concerning are long-period comets, which originate from the farthest reaches of the solar system. These icy bodies travel on elliptical orbits that bring them near Earth only once every few thousand years, making them unpredictable and harder to track. They also move much faster than asteroids, meaning they give us even less time to respond. Their impact would unleash far more kinetic energy, and with almost no lead time, evacuation or deflection would be impossible. The gaps in global surveillance only make matters worse. While agencies like NASA and ESA maintain robust observation programs, much of the southern hemisphere is under-monitored. Developing nations often lack the infrastructure to contribute to detection efforts, leaving large portions of the sky effectively invisible. Without a truly unified, planet-wide system, threats can and do slip through the cracks. Delayed political action is another critical vulnerability. Governments often wait until danger feels imminent before allocating resources or making decisions. In the case of a high-speed asteroid or comet, such hesitation could cost millions of lives. Combined with the chronic underfunding of space programs, this delay creates a ticking clock with no guaranteed response. And when the worst-case scenario does happen, society may face an unthinkable ethical question: who gets saved? Emergency plans will inevitably focus on protecting high-value regions, key infrastructure, and leadership. But with limited resources, the rest of the population may be left behind. This triage scenario, choosing who lives and who dies, could become a grim reality if the world fails to act now. The truth is sobering. We are making progress, but we are still exposed. And in space, there's no room for second chances. Humanity's odds. Are we prepared? Humans are notoriously bad at preparing for low-probability, high-impact events. It's a psychological blind spot. If something hasn't happened in our lifetime, we assume it won't happen at all. That cognitive bias is what makes planetary defense so difficult to prioritize. Despite knowing the risk exists, we treat it like science fiction, something that only lives in movies, not in our funding bills or national strategies. Our current preparedness level is a mix of promise and insufficiency. The success of NASA's DART mission shows that we can influence the path of an asteroid, but that success is only meaningful if we detect the object early enough. Right now, only a portion of near-Earth objects have been catalogued, and most smaller but still dangerous ones remain undiscovered. International cooperation is increasing, but the pace is slow and fragmented. There are global action plans in place. The United Nations has established organizations like COPUOS, the Committee on the Peaceful Uses of Outer Space, and YAON, the International Asteroid Warning Network. These groups coordinate data sharing, simulation exercises, and public education campaigns. They represent a vital step toward building a unified planetary response. But they are advisory bodies, not enforcement mechanisms. Their influence depends on how seriously national governments take their recommendations. The concept of asteroid insurance has been floated in scientific and policy circles. It's not about financial compensation but rather about preparing infrastructure, response systems, and evacuation protocols in case of impact. It's a smart idea, but like most preventive measures, it's underfunded and underappreciated. What can an individual do in the face of a threat so vast? The answer begins with awareness. Supporting science education, voting for leaders who prioritize space and science policy, and contributing to organizations that promote planetary defense are all meaningful actions. The public voice matters. When people care, governments respond. Sharing knowledge, funding research, and staying informed are the most powerful tools available to the everyday citizen. The technology to prevent a mass extinction exists. The knowledge is growing. But what's missing is a shared urgency. And in the fight against celestial threats, waiting to feel afraid may be the deadliest decision of all. A planet-killer asteroid may not strike tomorrow. But it will strike someday. The evidence is in our past, the threat is in our sky, and the future depends on what we do now. The universe won't warn us twice. Are we listening? If you found this video eye-opening, subscribe for more science that matters. Share this with others, leave a comment with your thoughts, and stay informed.